Last presentation for the day, which is from Saktivel Ramaiah. Saktivel is a senior principal design engineer at Cadence. He has 15 years of verification experience. Prior to Cadence, he has earlier worked at Synopsys and Tata Elxsi. He has masters from College of Guindy and bachelor's from NIT Trichy. Saktivel, please. Just a reminder to please vote for the last session, last paper which was presented.
To use this? Friends, back, this is French. Yep. That is the pointer. Good evening, everyone. My name is Shaktivel, and just to add about the biodata, so I have 15 years of experience, and in that 12 years I spent in USB controller IP verification. And I'm relatively new to formal verification. It is almost 1.5 years I was spent in formal verification. So with that background, I will go to the topic. And so I thank I thank DVCon for giving me this opportunity. And I thank the audience, being the last session, thank the audience for remaining here. So the topic is efficient formal strategies to verify the robustness of the design. Let me start with the defining what is robustness. So, so any design which exhibits a deterministic behavior for noisy inputs can be called as robust design. So with that, I will move forward. So I've just listed down the challenges faced by the digital, being coming from, even though I'm coming from the verification background. So with the interaction with the designer, I was able to list the challenges faced by the designer. And so any design architecture, which must be able to correctly handle the order of inputs and the race conditions, which occurs due to the asynchronous nature of the inputs. Okay. And so this is one of the challenge in the digital design architecture, especially in the receiver side of the physical layer of any serial data communication protocol. For example, USB, or it could be PCI, or it could be maybe protocol. And so one of the challenges is for the asynchronous nature of inputs. So the order of priority is one of the challenge, and then race conditions. The race conditions could be could happen within the same interface, which we can call it as intra-interface, or it could be among the different interfaces, which we can call it as inter-interfaces. And so if the specification is evolves, right? Say for example, the block with which I have taken for this presentation is coming from CXL controller. There is a block called orbiter mux. And in that orbiter mux, there is a block called VLSM. VLSM stands for Virtual Link State Machine. So, so around 1.5 years back, the spec was evolving. So it was switching from CXL 1.1 to 2.0, and a lot of changes in the orbiter mux chapter. So the designers and verification engineer was facing a lot of difficulties in interpreting the gray areas in the specification. So the formal has helped. So I will explain that how the strategies, which we put forth has helped us to list down all the questions, and then we can put forth, to the CXL consortium. And it will also help to identify the inconsistencies in the specification. So these are the problems, which are faced by the designer. So, so what are the solutions? So the formal verification is an excellent at highlighting such situations, provided the approach is systematic. Okay, and so I'm going to recommend two strategies for the verification engineers. The one is the positive negative, categorizing the assertions as positive negative assertions, and the second is effect without cause assertions. So we'll talk about that vividly, in later slides. And this for adapter for qualifying an RTL block, as I said, it was we were able to qualify a block, a VLSM block in the Cadence CXL controller. So this strategy is for basically helping us to exhibit the art of categorizing the assertions and showcase a systematic approach required to qualify the design and helps to bring clarity in the implementation specification. So what is the motivation behind to derive these strategies? So we all know that the sine wave is the worst disturbance a system can be subjected to, and it is used to verify the stability of the any system, right? And similarly, the square wave, the toggling input is a worst disturbance. Yeah, a digital design circuit can be subjected to, and it is used to verify the robustness of the design. Okay, so this toggling inputs, the formal tool takes care of the toggling inputs. In fact, it gives the exhaustive combination of inputs. And the role of verification engineer to derive the assertions, because the tool cannot derive the checkers. So it is a human being, the verification engineer has to derive all the checkers. So so we needed some guidelines or strategies to derive to make sure that the checkers are in fact exhaustive. Okay, so first I will start with the first strategy. I'm calling it as positive and negative strategy. And so each feature will be categorized as positive and negative aspects will be analyzed. So let's take an example. For example, if a specification states that, say, when a request packet has been sent, receipt of any other packet other than the status packet is considered as an unexpected packet. Let's say the specification states this. So generally, what we would derive is, what kind of checkers we would derive is, so that sends a packet, and it receives the status, and then whether the DUT has gone to a different state or not, or whether the DUT has gone to an intended state or not. That is one kind of check you will write. And another check is, say DUT has receives a request, and whether it has sent a status packet in a stipulated time or not. Okay, so these are the regular checks everyone will write. But these are essential checks but not sufficient, right? So we need to raise questions like, so what happens if an unexpected packet is received after a request? So what happens if a status packet is received without any request? So for these questions, the DUT in the high level, the DUT should have two options, right? Two kind of behaviors it can exhibit. The first thing is it can react to it. For example, it can initiate any request if there is an error. That is the first option. The second option is it can ignore it. So I'm just categorizing it in a very high level. So, but it has to be, our idea is that the DUT has to be deterministic, right? It should know when to ignore and when to react it. So let's consider this generalization here. So let us consider there is a signal X and a packet Y. So how I am categorizing is, the first point is X should be asserted or Y should be sent, or you can another one like for a particular state transition, we will be having P number of reasons. Okay, I'm just labeling for the easy understanding. And the second one is, let's say X should not be asserted or Y should not be sent, or no state transition for N number of reasons. Okay, so if you categorize in this way and if you list it, and so what it will transform is, so this P number of reasons will ultimately considered as positive checks and will transform to P number of assertions. And whereas the N refers to negative checks and transforms to N number of assertions. Okay, so I forgot to add example slide here. So I will try to explain this thing with another example. So let's take an example. Let's take the second point. Okay, so what happens if a status packet is received without any request? Okay, so let's take that an example. And as I said, there are two options, right, to that at the high level. Either it has to react to it. For example, it can initiate a retain request. And another option is it can ignore it. Okay, and let's say the implementation specific or standard says that you have to react to it. And so in that case, what you will do is, you will consider that as the positive checks. Okay, because you are reacting to it, and the implementation spec or the standard is defining that how the condition is it is going to drive an output, or it is going to transition to a different state or not, that the spec will define. So I'm not going to define that. So with that example, so the first category, I am terming it as positive check. I'm basically terming it as a positive check, and um, that so in case of this first category positive check, you give specific inputs and you expect the that to give a certain output. Okay, so that's how I'm categorizing it. So let's go to a case two, where in which the that doesn't react to it. Okay, it has to ignore the packet, or it has to ignore the input. Okay, so in that case, I am categorizing it as negative check. And so in case of negative check, we are basically giving a noisy inputs to the system, and then we are expecting the design to do nothing. Okay, so that I'm categorizing it to the negative checks. Okay, let me give another example in case of race conditions. Let's say you have three input signals, A, B, and C. And let's say these A, B, and C are asserted at the same time. Okay, and let's say the implementation spec says that the A has highest priority. Okay, so as far as the input signal A is concerned, we expect, let's say the A, B, C drives X, Y, Z, respectively on the output side. So as far as the, in this example, as far as the A input signal is concerned, you are expecting an X output, right? So this is the positive check. But as far as the B and C is concerned, B and C are also asserted, but you are not expecting the Y and Z to getting asserted, right? It should not reflect in the Y and Z. So that I am categorizing it as negative check. So I hope the categorization of positive checks and negative checks is clear by these two examples. So I'll move on to the next slide. So coming to the strategy 2, so strategy 2, I am labeling it as effect without cause. So in general, we would be having the cause effect feature checks, right? So where in which the inputs triggers an assertion to check an expected output. Okay, so that we can also call it as positive check. But that is, however, a disadvantage in having only this check. Okay, so what happens if there is an effect without any cause? Say, for example, if you have an unexpected a signal which got asserted, output signal which has got asserted, or unexpected transmission of a packet, or unexpected state transition. So this way we can call it as glitches or spurious or unexpected behavior of the DAT. So that time categorizing it as this unexpectedness, I'm categorizing it as an effect without cause. Okay, and so in order to ensure there are no unexpected changes in the outputs or state transitions or not transmitting any packets. So when there is an effect check, there was a valid cause. Okay, so I could give some examples like for yesterday I have experienced one thing in my laptop. So I just placed my laptop in sleep mode, and but after 10 minutes I was hearing some noise in the laptop. So when I cross-checked what kind of noise it is, I was seeing that cooling fan was running. So it ran for a minute and then it stopped. So this was not expected, right? When you put any laptop in sleeping mode, it should not do anything, right? And it will automatically consume the battery if the cooling fan is running. So how do you test these scenarios? When which you haven't given any interruption, the user haven't given any interruptions. The user has just put the laptop in the in the sleeping mode, but still it was working in the background. And so I was guessing what kind of logic would be triggering this kind of situations. So inside the RTL there could be some internal timers, okay, which would be running, and so once it times out or once it wraps, right, so that could trigger some logic, and then there is a possibility of misbehavior. Okay, so how do we catch those scenarios? So to catch those scenarios, we need to put the output as the input condition. So if you see the system log assertion, so before the implication operator, where we call it as precondition, you put the output as the precondition. So if there is any spurious output, any glitches, the assertion will trigger and it will cross-check whether the valid cause has been happened or not. So let me explain that with another example. So let's say the spec states that let's say the spec says that when active request packet is received in low power state, that goes to retrain state. Okay, very simple, feature. So when you look at the positive check or cause effect check, what you will generally do, any engineer will do is, so you will put the condition as, okay, I will receive the active request packet in low power state, and then I will expect, that goes to the retain state. This is a normal check we used to write. But the effect without cause check is something like, you can see as I stated before in an example. So the precondition, I am checking the DUT transitioning to the retain state from low power state. So that is the trigger to the assertion. So once that is done, I am basically checking whether that has actually received an active request packet or not. So, but to verify this negative checks and this effect without cause checks, you need a strong auxiliary code backup, because you need to model it, right? So when you see this transition from low power state to retain state, actually you need to the model code, in your formal ENV to understand that, okay, there is something active request packet has been already received in the intended state. So that kind of intelligence it should have to verify this cause effect checks and negative checks. So basically the idea is to break each and every feature and sub-feature, and basically I would say the divide and rule, that's what we need to do. And so these strategies will ensure that we leave no stone unturned in the design. So the implementation is very simple. So you have the formal ENV where the system Verilog module, top level is the system Verilog module, and you have instantiated that. As I said, I have picked a particular RTL block from the CXL controller IP, and it's called VLSM, Virtual Link State Machine. And so this IOs are sampled in another module called checker module. This checker module has all the assumptions and system Verilog assertions, and to back the system Verilog assertions, to have the intelligence for the negative checks and the effect without cause checks. So to have that intelligence to back those negative checks, so we have this auxiliary code here. Very simple architecture. So this particular this is the statistics I have from the project, and you can see the particular VLSM block has been picked for this project, and it has been exhibited using the Cadence Jasper FEB app. And to give the rough idea of the complexity, I would say it is not very much complex unit RTL block. I would say it is medium size block, in which you have 3,000 lines of code and 4.5K gates. So there were 250 assertions, and the full formal run runs for this around 5 hours, and so most of the assertions finish within 2 hours, right? 95% of the assertions finish in 2 hours, and 5% took more than 2 hours, and another 5% was got explored. Okay. So how do you sign off when something got explored? How do you sign off? You try to use the split case technique, and you will try to see the you will see the you will put the cover properties, and you'll see the number of clocks at which this this particular scenario is covered, and you'll compare with the number of clocks it got explored. So you'll compare that, and with the engineering judgment, you will say that, okay, is this okay, or this much deep it has verified or not. So that that is a pure verification engineer judgment. And so this 250 assertions, you can imagine 250 assertions means 250 features, sub-features, and with the category of positive, negative, and cause, effect without cause checks. So this has been listed in the vPlan, Cadence vPlan, and each feature has been mapped to this assertions. And after the formal run, the mapped assertions have been back annotated, and you can see the metrics. So that's how it has been signed off, in addition to the code coverage. Yeah, so we'll go to the next slide. So if you see the application, so these are all generic thing, nothing, it's not only related to the CXL controller, orbiter mux block. So you can easily associate this with any other RTL block you are working with. Okay. And so applying these strategies provide a structured thought process in analyzing the design or identifying the implementation specific gray areas. It could be implementation specification or it could be the standard. So I have just listed some of the questions here. So what happens if the DUT encounters any of these circumstances? So we were able to, so some of them we were able to raise it upfront, and certain cases where we are able to raise during this exercise, right? During this implementing these strategies, we are able to question it. So I'll just go through it. What happens if the DUT receives a valid package in wrong state? What happens if the DUT receives valid packets in a wrong mode? And what happens if it receives the back-to-back request? Basically redundancy. It could be a request or response. And so this is the race condition. It receives multiple requests at the same time. It could be within the same interface or it could be among different interfaces. And because the order of priority, the spec should give a clear order of priority. And so this is also, the last one is the receives packet with reserved values in the valid field or non-zero values in reserved field. So these are very basic things we generally miss out, in functional simulation. And due to the project, hectic schedule, we try to miss these basic items. So by employing this kind of strategies, you won't miss out, any checker items. And so this is something on the spurious case, when which the DUT sends a packet wrongly, in the wrong mode. It sends a correct packet, but it sends in a wrong state or wrong mode, and sending some redundant packets. Okay. So these questions and checks pave the way to have a deterministic and consistent behavior of the DUT for noisy inputs to make the product robust. And so there was frequent interaction with the designers. So I was posting questions based on this experience, so they were able to answer it from seeing the spec. But the gray areas, right, they were able to take it, the questions to the CXL consortium and get the clarity back. Okay. So coming to the conclusion, so adoption of the formal verification for critical submodules of the IP. It is particularly, so as I said, the CXL was evolving when I took up this project from 1.1 to 2.0, and there were a lot of gray areas, especially in the orbiter bugs block. And adopting these strategies was very much helpful in the interaction with the designer, and going, having a lot of, asking a lot of questions with them and getting clarified either from the standard or from the consortium. And the VIP, so the real use case of the formal is doesn't need any VIP, right? The VIP can happen parallelly, and it might have not reached, even if it is developed, it might have not reached maturity level. So the formal was very helpful in this. And the final point is, so the comprehensive approach described above of having both positive and negative, and of course the effect without cause checks in the formal environment has yielded a considerable number of bugs. So this, just want to tell you, so I have missed some point here. Yeah, so we were able, so with this 450 gates and 300 lines of code, so I was able to report around 70 plus bugs from this particular block itself. Okay, so most of them were basic, which are from the gray areas, and some of them from the corner cases. That's it from me. So we have published a white paper last year from Cadence, and so this particular portion has been picked from that. So I'm one of the author on that white paper. So this strategies were picked from this white paper.
Thanks,
Thank you. Any
Saktivel.
questions?
Questions for Saktivel? Okay.
Shaktivel, you were talking about sine waves and square waves for verifying it, right? So, I mean, you could generate the stimulus for sine waves and square waves, or it
No,
was
that is
post-fiction?
just for motivation, for the
Okay.
thought process.
Okay.
So the, as you know, the square wave is the, the worst disturbance yes, digital design has been subjected to, right? So the formal, if you see the formal, it will really toggle. I mean, it is not a signal. We should not imagine in that way. It is a mathematical model, but it will go for all the combinations, right? So it is virtually, it is toggling. So it will subject the design, that kind of noisy or toggling inputs. So that is on the input side, the tool is taking care. But as a human being, as a verification engineer, how do we make sure that the checkers are exhaustive? So the code coverage alone doesn't guarantee, right? So if you have three states, say S1, S2, S3, and if the designer has missed S3 itself, the code or tool doesn't have the intelligence to find the S3 has been missed. So you need to bring that to the functional coverage. And you need to, as a human being, we need to bring that in as part of the functionality. So that's what I've just put it in the motivation slide.
Okay, thank you.
Thank you.
Yeah, any other question? Thanks, Saktivel. May I request Vichal to hand over the certificate?
Okay, yes. Okay. It's a long time. Thank you.
Thank you very much.